the power rule is probably the most basic of the differentiation rules. It allows us to take the derivative of a polynomial very easily and very quickly. We're going to mix the power rule with sum and difference rules and constant multiple rules, and we'll get to those tomorrow. We'll start talking about those tomorrow. But the power rule is one that allows us to take the derivative of something like x to the n power for any n. We're going to kind of walk through a proof, kind of a skeleton of a proof at least, for when x is an integer, specifically a positive integer. But then, because of Newton's binomial expansion theorem, which says that the binomial expansion is actually a continuous function and not a discrete function for just integers, but it also works in between the integers and for negative numbers, the proof could be expanded to include any exponent except when, except in one special case. And we'll talk about this special case later. So if we wanted to take the derivative of x to the n, and keep in mind, in this case, n is going to be a number. So like x squared, or x to the 9th power, or x to the 427th power, whatever you want n to be. This is what the limit definition of that derivative would look like. So we would want to evaluate the limit as delta x approaches 0 of x plus delta x to that nth power minus x to the nth power divided by delta x. And so the trick here is being able to expand this binomial here. You guys remember how to do that? Yeah, we're going to use the combinatorics here. So this is going to be the limit as delta x approaches 0. If we want to expand this binomial here, it's going to start out as x to the n plus, so the first term is going to be x to the n, right? You guys remember that?
Yeah.
And it's really n choose 0 times x to the n times delta x to the 0. But we don't need that delta x to the 0 because that's 1, right? And n choose 0 is also going to be 1. There's only one way to choose 0 things. So then the next term is going to be what? Anybody remember?
N choose 1. X to the n minus 1. And then delta x.
X to the n minus 1 times delta x to the first. Okay. Then the next term is going to be
N choose 2.
n choose 2. X to n minus 2 delta x to the second. Okay, so the pattern here, this number here, and this number here are all going to be the same. So the general term for this is going to be, I'm just going to write this down at the bottom, is going to be n choose I times x to the n minus I times delta x to the I. Right? You guys agree with that? And that's going to go all the way till when I is equal to n. And so we're going to have n choose n, which if you have n objects and you want to choose all 10 of them, there's only one way to do that. So we end up with a 1 here at the end, times x to the 0 times delta x to the n. And that's going to be your last term. So I'm going to put some ellipses in here. Show that pattern is going to continue. And then the last term is going to be n choose n times x to the 0, which I'm going to just leave off, times delta x to the nth power. All right, and that's what we're going to end up with in the numerator. So this is what we get for the expansion of x plus delta x to the n, but we also have our minus x to the n here, right? So we can't forget that. That's kind of important. In fact, that's really important. And then that's all going to be over delta x. All right, so right off the bat, there's something that we can simplify here, which would be what? Yeah, so those x to the n's are going to cancel each other out. So those are gone. And you'll also notice that every term that's left is going to have a delta x in it. So we have a delta x here, delta x squared here, delta x cubed here, all the way up to delta x to the nth power here, right? So that means that we can factor out a delta x from there. So when we do that, we're going to get something that looks like this. The limit as delta x approaches 0 of delta x on top times the quantity, and then we're going to have n choose 1 times x to the n minus 1, and no delta x there in that one, plus n choose 2 times x to the n minus 2 times delta x, and so on and so forth, until we get to the last term, which is going to be n choose n times delta x to the n minus 1. Okay, so we've got that in the numerator all over delta x in the denominator, right? All right, what's going to happen with those delta x's then? We can cancel those, and we can only cancel those because we know delta x is not 0. Okay, it's approaching 0, but it's not equal to 0, so we can do that. Now, what do we have left? What's going to be, after this first term here, what are we going to have in every term after this? We're going to have a bunch of zeros, right? Because we have a delta x here. Then the next term is going to be delta x squared. Then the next one's going to be delta x cubed, all the way up to delta x to the n minus 1. And so when we plug delta x in, or when we plug 0 in for delta x, all of these terms after the first one are going to become 0. So that's going to be 0. These are all going to be 0 here, and this last term is going to be 0. And so what we end up with is, we can take the limit off now because we plugged 0 in for delta x. We end up with n choose 1 times x to the n minus 1. So the only question we have left to answer is, what is n choose 1? So if you have n objects, how many different ways can you choose one of them? N. And those of you that are taking physics right now, in the second year of it, does that look familiar?
Yes.
That's the power rule. All right, so we use the limit definition and we generalize it for any exponent. I did say at the beginning, with this proof, with this version of the binomial expansion, we're assuming that n is a positive integer. If n is, say, some rational number that's not an integer, or even an irrational number, or a negative number, the binomial expansion is going to look a little bit different. But Isaac Newton, who's a pretty smart guy, showed that the binomial expansion actually ends up being continuous, so it doesn't just have to work for integers. And so this is going to be true even if this is a fractional exponent. So this works even if it's like x to the 1/2, which would be the same thing as the square root. So we could use this for square roots and other roots, not just integer exponents. So what this is saying is the derivative of x to the n, we take the n and multiply it out front and subtract 1 from the exponent. So the example that I gave you earlier, x to the 9th, what would be the derivative of x to the 9th? 9x to the 8th. So we would take the 9 out front, subtract 1 from the exponent. Okay, you guys, most of you at least knew that already from your physics class, right? Okay, so this is the power rule.